please. So Jeremy kind of inspired me to give this talk in the way that I'm going to give it. So I wanted to give a talk. I wanted to tell you about these problems. But when Jeremy was introducing himself the other day, he said, I'm a mathematician who works in a philosophy department and I do computer sciences. And indeed, that puts me thinking about the fact that I think that mathematics right now is kind of in a very special moment where we need to combine these three aspects of the mathematical work to help us continue in the right direction. So what do I mean by that? Well, so I think that often mathematics develops like this. Well, there is first some philosophical consideration that influences a mathematical program. And then once you have this program, you can do mathematics. And well, the kind of mathematics that interests me is very close to at least theoretical computer and computer science. I will just put them together because I think that their development in this part of the mathematics is often, not always, but is often in parallel. Well, yes, I forgot to say that, like Jeremy, I also have an interest in philosophy. I'm an associate member of a center for philosophy of sciences and technology, which is called the HSTP. A few years ago, I think, I met Jeremy while he was giving a talk about the latest achievements in Lean at that time. So, so this kind of vision is shared by people who work in that center, and I'm happy to collaborate with them. Well, so not all mathematicians will agree with what I wrote here, and I'm not claiming that all mathematics has been developed like that. But let me give some examples of things that are close to our hearts that have been developed in this way. So let me just give some examples. Let me start here in Germany, but even if I were not in Germany, I will start by Hilbert program. I think Hilbert was not the best mathematician per se in his time. That's what he said. He said that Minkowski was much stronger than him in mathematics. But he had a much broader vision, and that made him actually the best mathematician of all times with time. So he had this program which was sort of a philosophical program of formalizing mathematics. And well, even though it didn't work out the way that he wanted to, that brought lots of mathematics. So some of the things that it brought about was the development of first-order logic, including the completeness and soundness, which were proven by a philosopher in the PhD thesis in philosophy by Gödel. And of course, the incompleteness theorem by Gödel is also an example of that. And what else I wrote here? Yes, so the development of a Turing machine. Well, computers come out from Turing machines. You may even say that they come out from Leibniz's consideration a very long time ago. But these were theoretical considerations in logic, in philosophy, that brought this out. So there are many other examples, which I will not state. Perhaps I'll just mention the classification theory of models in first-order model theory. I think it also fits in this framework. So much research in mathematical logic has been devoted to completeness of first-order logic, which was used in subjects such as model theory studying complete theories. And completeness is essential for development of forcing in set theory, which is my basic subject. So this is something that has been very much researched. What we are talking about in this workshop is more about soundness, verification of proofs, are the proofs that we do actually sound. So for me, all of these things form part of mathematical logic. So somehow I see mathematical logic as a subject that feeds into mathematics by so logic sort of gives a framework to mathematics. And then mathematics develops more and gets out of this framework and needs more logic, so it feeds back into logic. So mathematical logic is very much inside of this. Not all mathematicians are logicians, and they don't need to be. And of course, there are subjects of mathematics where logic is perhaps even invisible to the people who practice it, but this is from the point of view of a mathematical logicians how things look like. Okay, so now, having taken this view, how do I see where we are in how will mathematics and mathematical logic look in the near future? How is this interaction going to be developing in the near future? What are our needs? Well, I think you are all aware of this talk and the speech, kind of mantra by Vygotsky, who entered into mathematical logic from a very hardcore mathematics because he felt nobody was reading his proofs. And he was really worried to start publishing wrong proofs. Well, not with no reason, because one of his famous proofs was found to be wrong a few years afterwards. It was before the Fields Medal. There are many important wrong proofs around, and this is very uncomfortable in mathematics. We start to be doubting our own soundness, and I think this is where you people come in with the formalization. So we really need a better way of verification in mathematics. So you know much more about this than I do, and I won't be bothering you by the technical details, but what I think and hope that will develop in the near future is that proof checkers will become usable tools for everyday mathematicians, the ones who can hardly type their emails. And how are they going to use them is to check parts of their proofs where they themselves have a doubt. Because whenever you make a new proof, you know that certain things are clearly true, but there are parts where for a long time you have a doubt, and it would be very comforting if you were able to check them in some way that is easy for you. I don't think it is realistic to think that mathematicians will learn how to use any of the existing proof verification assistants. Even the most enthusiastic ones will not. And I think you know this because those mathematicians who have learned these things have sort of stopped doing mathematics and have gone into doing formalization. And so I think the two together are too much of a, with some exceptions of course, like Peter here or Jeremy, but they are too much of a specialty to keep in one's person's specialty, okay? So I think that's one thing that we can hope. Another thing even further is to hope that the addition of papers publishing papers will have some use of proof verification. As a journal editor, often we receive papers and we send them to colleagues who say, basically, well, do you think this makes sense? Should we referee this paper? So we have come to that point in publishing papers that we don't even referee them before rejecting them. This is unfortunate, but this is because we just don't have enough referee power. And for many reasons, it would be good if an editor could just, if the paper were to be written in a way that says, okay, these are the most important new points that really should be checked before deciding if the paper should be refereed. And then the editor could somehow run some sort of formalization, or maybe even the author would give a formalized version of these points. So these are, I think, very important points for the development of proof checking for verification. Now there is another aspect where we also need help, and this is not yet there at all, and it's developing sort of in parallel to this community. I think there is, I hope there will be more communication between the two, so we need proof assistance. So I do not believe that mathematicians will become obsolete, but because some of the more theoretical deep theories I do not think can be developed in any sort of automatized way, but inside of these very deep theories, I think there are often parts that need to be checked and maybe cannot even be checked by a human because there are too many possibilities, or maybe even if they can, they shouldn't be checked by a human because there isn't really anything interesting that will come up. Calculating the Ramsey number of 6, for example, I think is not a particularly, it's not likely to give any particularly new knowledge, but could be done by a good computer and would be an important theorem. So this type of things, I think, can be developed, and I think it is within our reach. So these are things where there is some mechanical way of checking a number of cases, large number of cases, by a small available number of methods. And so that is what's being done today by artificial intelligence to some extent. But that's what they aim to do. And well, I think these two communities seem to be somewhat disjoint. Your community, I think, is much more aware of the other community than the vice versa. Perhaps because they somewhat arrogantly think that if they develop some sort of large language model that will prove a theorem, people will believe them it's a theorem. But nobody will believe them if that's a theorem if people cannot check it by other means. We don't even believe what ChatGPT says about Mirna Džamonja. Probably it says, I don't know, a French mannequin or whatever. So it is not reliable, and it needs to be done developed in parallel. So, well, what can a mathematician do to kind of help this development that is for our benefit? How can we influence what specialists like you or those AI people do? Well, if we are top mathematicians like Terry Tao, we can influence just by telling others that this is important. So this is I think excellent that top mathematicians like Kevin are getting interested in this, Terry and Dowers and so forth. I think that Terry Tao is the closest to this vision that I have just presented, and he has spoken about this, and his blog is full of things that can let you check this. Okay, but if you're not Terry Tao and you don't have a million people hits on your blog, how can you help or get engaged in this kind of development? So I have perhaps thought of what I can do to help this So the first thing that a mathematician can do is to understand the real state of things and then perhaps suggest some mathematical problems that might be amenable to the development desired. So what are the two observations that we can make in this? So difficulties observed. The first difficulty that is observed is that automatization is difficult. So going from this direction to that direction, today Jeremy was telling us about this new library. He wants to have, what is it to be called, LPLP, in which people will be proposing small lean programs to work on, sort of problems to work on. Well, these are not theorems, these are problems of a working lean formalization type. And he mentioned automatization is very far from giving actual proofs. I have a paper with Larry Paulson and Angeliki Kutsak-Agiraki, and I'll tell you a little bit more about that paper in a moment. But the conclusion after working in Isabel for those few months is that automatization is really difficult. And this is Laurie Paulson working in Isabel, and this is somebody who really knows this proof assistant, and this is a very suited proof assistant for what we were doing. So this is one difficulty. Another difficulty is it requires a lot of human power. To write these libraries is immense. Well, so Kevin is doing his bit of it by applying for numerous grants, employing young people on these grants to do formalization and so forth, and so other people. But I believe that this source of people is probably not sufficient for what is needed. Well, perhaps I'll tell you some suggestions of how one could go about this in a different way. But let me first talk about this part, which I think I have more to say about. So because automatization is difficult, I think it's very, very important to choose which problems to work on. Of course, it's very exciting to go and work on condensed mathematics or something, really important like that, big thing, sounding important. Well, I don't know it well, so I cannot really say how much it's important. But anyway, some big program of some very important mathematician. But what it is about this is that it's I think it's too hard because it requires a lot of training to learn, and it's hard to test. I think it's actually better to choose something simpler to start developing this direction. So what does this mean? So first, what we need to develop automatization is to think about training and testing. Training and testing are two different things that have to be done in this kind of subject. And there are requirements that are somewhat different for the two. So for training, we want to be working on non-mathematics. For testing, we need to be working on new mathematics. That's the real test, to prove something, even if it's small. So what kind of mathematics could fit into this? Well, it seems that what we don't want is that people for this step have to spend 7 years learning the subject in question. And also for this, the same thing is that new theorems should be sort of at reach of those who work with it. this was the philosophy of Erdős. Erdős, who is, I had the privilege to know Erdős, actually, quite well, I would say. I met him when I was very young. He came to talk to the Epsilon. The Epsilon were young mathematicians going to mathematical competitions. And then I met him again when I was a postdoc with Cellach, and at that time he still wanted to learn forcing. That was kind of his running interest. Yeah, because the system is quite complicated, but I'll try. So what was Erdős' mantra about solving problems? How did he train all these little epsilons who later became Laszlo Lovas and Semeredi and Miklos Latkovic and so forth? How did they start? Yes, yeah, I know you have
the other side.
Yes, yes, to try. Yes, I will. But now I'll talk a little bit. Okay, so Miklos Latkovic actually wrote a book about this. And this book is, I don't know if you know who Miklos Latkovic is, but he works in kind of set-theoretic analysis, and he also ran, I don't know if he's still involved in that, something called the Hungarian Semester of Mathematics. Where young, clever undergraduates go and spend one semester in Budapest and learn this sort of Erdős approach. So the approach is called conjecture and proof. That's the name also of Latkovic's book. And the whole method is that the conjecture should be easy to formulate, easy to test. You have a wrong conjecture, you go back, you test, and at the end you have a proof of something. So this is how you train young mathematicians. I've been teaching a long time in many countries. And I think this is the most successful way of training mathematicians. It's not maybe a more successful way of training those unfortunate people who have to sit in the calculus class. But those who actually want to learn the subject, this is great. And I think this means probably that this is the best way of training proof assistants. Just treat them as if they were humans. So the kind of mathematics, not every kind of mathematics is let us say, compatible with this method. If you want to do algebraic geometry, well, you better first learn about Grothendieck universes and complicated things. So this is not something you can do as an undergraduate mathematician, and you probably cannot do this as an undergraduate proof checker. As our proof checkers are maybe not yet undergraduates, they are still babies. So it seems that it could be that we teach them something that is amenable to this method. So what is it? It's, well, I think the most amenable, at least among the mathematics that I know, is finite and infinite combinatorics. So infinite combinatorics these days is not mentioned very much because it's a subset of set theory. But there are parts of set theory which are not at all amenable to this. If you want to work on Wooden's omega conjecture, well, first you will spend a few months to understand what the conjecture says, and then I don't think this kind of set theory is amenable. But infinite combinatorics, something that tells you really some easily understood combinatorial properties of easily defined objects, is amenable to this. And also, well, I started thinking of these things a long time ago. I told you I have this paper with Larry and Angeliki on a very particular subject, which I'll tell you about. So it was published already a few years ago. And I'm very pleased that others who work in this kind of philosophy have taken up this same idea, because there is this project called AIMO, Artificial Intelligence Mathematical Olympiad, which offers $10 million for a development of an AE model that would be able to solve mathematical Olympiad questions. So maybe probably many of you know what these questions are like, but as somebody who did this Olympiad, let me tell you what is, in my opinion, what these questions are like. These are very hard questions, they are terribly hard, but they require very little knowledge. And if you can do them, you can do them in a short time. That is, you know, you're not going to have 5 months to solve a mathematical Olympiad question. It's a competition. You sit there, you solve the problem. So this is a particular kind of mathematics, and there are people even in that part of the world that specialize in developing these kind of mathematical Olympiad questions. The other day I met with, on Zoom with a group of us. That was my first conference when I was 12 and a half. And imagine somebody put us together and even found one of those professors. It was called a summer school for young mathematicians. And we mostly became mathematicians all over the world. Valeria would be pleased to see how these young mathematicians were, because they were half women. There was complete parity, including the winners of these prizes. So, okay, so this is kind of a skill, and they, I think, are right to be focusing their attention on this. But this is a skill that interested me at that time, doesn't interest me anymore. So what does interest me now? Which is slightly similar and slightly different. These are solved problems. The person who proposed the problem has a solution. That's something that you get tired of solving. It's like playing chess. It's great to play chess, but you know the solution exists and it's there at finite time. It's not like doing mathematics. Mathematics is about open questions. So is there an area that at least I know something about that could be similar, but okay, so I thought about this and I came up with an area which I think is very interesting and we know very little about it in the place where we should really know much about. These are countable ordinals. Countable ordinals, of course, form part of set theory. Ordinals in general are very interesting, but the countable ones happen to be even more interesting. And let me tell you, the set theorists do not know anything about them which wasn't already known to Cantor, and a few people were after him. It's a shame. We developed many different methods for dealing with cardinals, large cardinals, forcing, amazing methods in set theory, but we can solve basically no problems about countable ordinals. Okay, so maybe I'll tell you now about some of my own work, but maybe not all of you actually know what ordinals are. There are young people in the audience, so let me just give you a definition of what ordinals are. It's a simple definition now, but it took some time to come up with. Cantor, for example, didn't have the right definition of ordinals. And as far as I know, maybe Peter knows this work better, Hausdorff also didn't have the right definition of the ordinals. He used Cantor's definition. The definition that we use now is due to von Neumann. It was his PhD, part of his PhD thesis. And it basically boils down that you can define the ordinals like this, by recursive definition. So the empty set is an ordinal. Then the thing is, if alpha is an ordinal, then so is alpha union the singleton alpha. And if A is a set of ordinals, then the union of this set is also an ordinal. Usually the ordinals are defined differently, and then these are shown as properties, but you can just define them this way and then show the usual definition as a consequence. But for this public, I think this is the easiest ever definition. You see recursive definitions all the time. And what does it mean to be countable formally when an ordinal is countable? If it's a bijective with a subset of n, the natural numbers. Okay, so why are these things interesting? Definition like any other, but where do they actually come in real life? Sorry. Well, first of all, let us make some observation about them, which actually form what is the usual definition of the ordinal. Okay, so observations is, the first one is that you can order ordinals by saying that alpha is less than beta if alpha is an element of beta. And it turns out that this is a linear order, which in particular satisfies that no ordinal has an infinite decreasing sequence of elements below, and also the totality of all ordinals, which forms a proper class ord, is linearly ordered by this order, and it has no infinite decreasing sequences. So there are no infinite decreasing sequences either in any of the specific ordinals or in the class itself. So this we call well order. These two conditions together are called well order. And this condition on its own is just called well-founded. You can study it also in the context of partial orders such as trees. Okay, so we have this, and then what are the facts? Is that actually there are not too many well orders in the world. This is a celebrated theorem of Cantor. So these facts are just proven in ZF. You don't need the axiom of choice to prove these basic facts about ordinals. The first one is that every well order is order isomorphic to an ordinal. And then over ZF, the axiom of choice, which you might know in one of its many equivalents, is actually equivalent to saying that every set supports a well order. And this is the basis of the theory of cardinals in set theory. So most of set theory is more interesting if you assume the axiom of choice, so you can deal with these cardinals, and there's much. In set theory, we mostly work with cardinals. Well, I'm not saying we never work with ordinals, but somehow our main techniques are about manipulating cardinals. Now, how about the ordinals? Who uses countable ordinals? Or any ordinals? It turns out that countable ordinals are quite interesting to people who want to rank proofs. So somehow you want to decide how difficult the proof is. So probably you know much about this because you worked about proofs. you work in proofs, but let me just mention a couple of ways that this can be used. So the first is a classical thing started by Gensen. It's called ordinal analysis. And what this does, it assigns an ordinal, usually a large countable ordinal, an ordinal to a theory. And the definition of this ordinal is quite simple actually, so I'll tell you what's this. So you can, using the axioms of ZF, prove that no ordinal has an infinite decreasing sequence inside, but you need ZF. So you need to be working with this totality. Okay, so if you're interested in theories that are weaker than ZF, this proof is going to be within, perhaps not within your reach. For example, if you just work witin piano arithmetic, you won't even be able to define all the ordinals. Talk about them. So you will be seeing a picture, a part of the picture of the ordinals within your theory. And so there will exist the following ordinal. So there will be some ordinals alpha such that T proves, your theory proves that alpha has no infinite decreasing sequence. Okay, I'm giving a somewhat simplified definition here, but this is more or less the definition. Now you can take the soup of all these ordinals, and that will be another ordinal, the union of that set of ordinals. The soup is just the union. And this is the ordinal that you attach to T. So this is the proof theoretic ordinal of T. And the idea is bigger this ordinal is, stronger T is. So Gensen proved that X, who is the one who thought about this comparison, proved that epsilon 0, the countable ordinal epsilon 0, is the proof theoretic ordinal of piano arithmetic. So proof theorists work a lot with this type of analysis. And this is a very important, ordinals are very important in that. Now, let's move to computer sciences. In theoretical computer sciences, people study a lot of trees with no infinite branches. Also in set theory, but we study bigger trees as well. So these trees are called well-founded trees. And when you have such a tree, you can assign to it a rank. A rank is an ordinal. So what do? You have this tree. I'm thinking of trees with the root. Okay, so here's the root. And then you have some elements, more elements, bigger levels, and so forth. But there is no infinite branch. So any branch is finite. So now what you can do is you look on the top, all of those elements that are on top, the terminal nodes, and they are incomparable with each other, you assign to them rank 0. And then you go down. The ones that are just below them, like these ones, they're parents. That you assign to them rank 1, and so forth. So what you do is that you assign to any element the supremum of all the ranks of the elements that are bigger than it in the tree, plus 1. So you see this rank is a function that will have a value, ordinal value, and that it will actually have the biggest value at the root. And this rank of the root is what's called the rank of the tree. So now you can compare various trees by comparing these ranks, and this comes very handy in for example, the study of WQOs. I'm telling you what WQOs and also why they are interesting in computer science. We have much history in mathematics, but they also have even more history these days in computer science. So you may say this, so what's the definition, what's the intuition behind these WQOs? You may say that the nicest thing about the ordinals is that they do not have infinite decreasing sequences. But on the other hand, a somewhat less nice thing about ordinals is that there are so few of them. They are just given by that recursive definition. So you might find there are other objects that have some order on them, which do not have infinite decreasing sequences. Well, okay, so you could take a very stupid example. You could take a long chain of points in which no two elements are comparable. You can call this a partial order. And certainly it has no infinite decreasing sequences. It has only decreasing sequences of length 1. So this is not very interesting. So let's try something in between. So let us look at the following thing. It's called partial order. It's a partial order which has no infinite decreasing sequences. And, so not to make it trivial, it also has no infinite antichains. So clearly an ordinal is a WPO, but there are other examples. For example, one that was considered by Higman, so at the beginning of the 20th century, is you look at the product omega times omega, Cartesian product, and you order the elements by saying that so these are pairs, x, y, and x prime, y prime. You can order them coordinate-wise, and you will have a WPO. There are many more complicated examples. And what's this? That in fact, once you have these two properties, you can associate to this object a tree. Many trees, actually, different trees. For example, you could look at all decreasing sequences ordered by extension. Of decreasing sequences ordered by extension. And this is going to give you a well-founded tree because there is no infinite branch in that. So this tree will have a rank. The rank of this tree is called the height of your partial order. So it's some ordinal. Then you could look at the tree of incomparable elements, incomparable sequences of incomparable elements. And again, you are not going, it's going to be well founded. Also ordered by extension. And so this also will have a rank. This rank is called the width of your partial order. Or you can say, well, okay, let me start looking at linear orders. So if we adapt the axiom of choice, then every partial order can be extended to a linear order. And since the partial order has no infinite decreasing sequences, any linear order that extends it will also not have any decreasing sequences, so actually it will be an ordinal. So all the linearization of such a partial order are ordinals, and you can look at the biggest ordinal that you can reach, the supremum of all such ordinals. And it's a very nice theorem of Descartes and Young that the biggest such ordinal exists. So you look at all the linearization of such a partial order, There actually is obviously supremum, because this is just a set and there is a class many ordinals, but the supremum is actually a maximum. So this is called the maximal order type. Maximal order type of a minorization of a WPO exists. So this is the theorem. And this is the ordinal invariant that's called O. So now you have three ordinal invariants that somehow characterize your partial order. And as you can imagine, you can use them as a complexity measure of the partial order. So bigger these ordinals, more complicated the partial order is. Okay, great. It doesn't perhaps that exciting. But let me tell you why that's used in computer sciences in theory of verification. So in verification, they look at transition systems. So transition systems are nothing else but simple systems where you have a set of states and a transitions. So like a finite state automaton is a transition system. Many other examples of such systems in theoretical machines are transition systems. So when you look at them in this kind of generality, something like this, transitions. An immediate question that comes to mind is the halting problem. So once you start from a certain configuration in your state, and you apply the transition, is the system going to converge? Are you going to halt? So now, if this relation is in some sense guided by WPO, then this problem is solved, because if you define this correctly, you get what is called well-structured transition system. Let me just write this definition. Is you introduce some WPO on S, called less or equal, and you require that you have this kind of thing. If S1 you can reach from S1 to S2, and S1 is less than T1, these are states, then you can find, maybe by applying a few times this relation, so I'll put a clean star there. So in some finite number of steps, you can complete this diagram. You can find a T2 that you can reach from T1, such that this S2 is less or equal than T2. So if you require this kind of diagram, compatibility between your WPO and your state system, then this transition system immediately gives you the backward coverability. It gives you the decidability of the coverability problem and other termination problems. So this gives decidability of termination. So these things are very much used in verification. And, well, I won't go into the details, but big prizes were given to people who invented this. So this is an important subject within verification. Some names to remember are Abdullah and Alain Finkel. Okay, so this is how WPOs come to be interesting to computer scientists. There are some other reasons, but they are interested therefore in these measures of complexity. Great, so now we have a very concrete problem, interesting to people. How easy is it to solve? For example, look at the problem of having two ordinals, alpha and beta, and you look at these products alpha times beta. What can you tell us about the width of this partial? Can you give us a formula? It turns out that in one of his very first papers, Uri Abraham found a recursive definition, recursive formula for this. It's very long, I'm not going to reproduce it. It's a very complicated formula which exists. How about 3? That's a PhD thesis of a student called Lisa Hilliard. 4 we don't know. So we don't know how to solve this problem. What are the techniques that are involved in this? There is basically only one technique in checking many cases. This technique depends on something called Cantor's normal form. What Cantor's normal form, as the name suggests, it was developed by Cantor, so it's a technique that depends on things that were already known in the 19th century. It says that every ordinal can be written as a finite sum of some power of omega. I didn't tell you what the powers are, but omega is the ordinal corresponding to n. Then some finite number, and so forth. Something like this. So every ordinal has this form, and almost all the proofs, or all the proofs that are in this subject are in one way or another related to studying possible forms, Cantor-normal forms. By hand, it's very long. It's case analysis, but it's something that I think could be developed. Isa is a student who is finishing this 4th of July or 3rd of July in the NS Cachan, Paris-Saclay, and has done some experiments in Koch in her thesis, but I think much more can be done about this type of questions. This is one of the type of questions. Let me tell you the question that you worked on with Maria and I. Oh yeah, I forgot to say that Stefan Schmitz and Philip Schnobel and myself wrote a large paper about these ordinal invariants in which we could do many different things with them. But that's the open question from the middle. Okay, so what I wanted to say, if you have omega, you color pairs of omega into 2 colors, into 0 and 1. There will be an infinite subset of omega such that all the pairs are colored in 0, or an infinite subset such that all pairs are colored in 1. Let's try to do this with an ordinal. So you take an ordinal, you color the pairs of the ordinal into 2 colors, and you want to recover this result. It's not going to work out. The best you can hope for is to have the following. Either you have a 0 chromatic subset of order type alpha, or 1 chromatic subset of cardinality 3. This is the best you can get. And in 1956, Erdős asked to characterize countable ordinals alpha that satisfy this property. This problem is still open. Jean Larson is the one who did the most for this problem. I think devoted her almost the entire career to this. She's retired now. And with Larry and Angeliki, we formalized a paper of hers from 1975. It took us 6 months. That's the very beginning of what is known about this. And all that's known is very combinatorial. It depends on things that you do by hand. Jean had an infinite vision. So like if we compare her with a chess player, she would be Kasparov, I don't know, somebody who can see a lot of positions in advance, not given to ordinary mortals. But I think this is something that good formalization could solve, actually. So that's what I want to say about mathematics. I also wanted to say something about the manpower. I know some people who work in industry, in AI industry actually, and their idea is to outsource to less rich European countries. So I was just recently in Bosnia. There's a company in the United States that outreaches programming tasks to young Bosnians. It's good for them, it's good for the company. There is the program of the European Research Council called Videra, which gives lots of funds for such scientific ideas to develop things in the European Union, or outside of the European Union, but in countries that need development. There are many such countries in the world. I just wanted to mention this as a possibility of how you could get more well-educated manpower to work on formalization if you work on applying for such programs.